Okay, let's go ahead and get started. You guys can hear me okay? Okay, so we're going to cover 7.1 today. And then the remainder of the time, I'll just answer homework questions. I'll put us into some breakout rooms if Gabrielle shows up and does tutoring with me. So we'll go through 7.1 and then I'll just field homework questions from then on. Okay. Okay, we do have an exam coming up. Next week is kind of weird. Next week we do not have class on Tuesday. That following Thursday, a week from this Thursday, will be our exam. The exam will be in Canvas. So it will be under quizzes for the exam. Okay, and it's exam 2. It will be done during class on that day. You'll have 3 hours to do it from 6 to 9 to answer 20 questions. They're multiple choice questions, 20 multiple choice questions, and it'll be available on the 2nd, which is a week from today, week from Thursday. Today we're going to end chapter 7. And yeah, I was just about to answer that question, Jennifer. And then on Thursday, I'm going to go over the review. Okay, I sent out the review and the solutions, but I'll go over the review and how to get those solutions on Thursday. Okay. Okay, any other questions before we begin? Okay. Okay. Okay, so let's go over 7.1. If you can't see what I'm doing or you can't hear me, let me know. Okay. Just send me a chat, it'll come up in as a notification. Okay. Okay. Okay, 7.1, what are the objectives? Okay, the first one, state and apply the central limit theorem. So I'll discuss what the central limit theorem means and determine the shape of the sampling distribution from means and proportions. Okay, number 2, calculate the mean and standard deviations, or what we call the standard error. Okay, for the means. Go to here. My pens, 1 second. There. Okay. So the standard deviation, which is the standard error of the means and the proportions. Okay, define the sampling distribution and use it to calculate the probabilities. And then we're gonna do this for means and proportions. Okay, define the sampling distribution and use it to calculate probabilities involving the sample means and sample proportions. So there's different rules for means and different rules for proportions. Okay, explain why the sample means and the proportions are good estimators for population means and population proportions. Okay, why are the sample means good estimators? Sample means and sample proportions are good estimators. Okay, so how does that work? Okay, why statistics? We use data from samples to make inferences, okay, or good guesses, okay, about a population. Okay, it's kind of like a hypothesis, which is an educated guess. Okay. For example, what is the mean height of all US adults? So we wouldn't be able to survey all of the US adults. What we would do is we would sample a bunch of them, and then we would make an educated guess based on the sample, okay, based on the sample size. Okay. Okay, we need a reliable way of estimating a population parameter. It needs to be both accurate and precise. Just make sure everybody can see. Always concerned. Oops, I exited out of Zoom.
We're still here, Professor.
Okay, I don't know why it said I had exited out. Okay, thank you. Okay, so both accurate and precise. Okay, so what's the difference between accuracy and precision? Okay, so we could be accurate, okay, but not precise. Okay, that means that we're actually hitting the board, okay, but we're kind of all over the place. Okay, the target is the center, and we're kind of all over the place here. That's accurate, but not precise. Okay, we're hitting the board, but they're kind of all over the place. Okay, so then there's precision, precise but not accurate. Okay, so what is precise but not accurate? Well, it'd be not hitting the board, but okay, they'd all be grouped. Okay, they'd all be grouped together. That's precise, okay, but it's not accurate. We're aiming for the center here, and we're missing the mark. Okay, and then there's not accurate or precise. Not accurate nor precise. Okay, and that would mean that they're off the board and they're way off. They're way off from each other. Okay, not accurate nor precise. Okay, and what we want is we want accuracy and precision. Okay, we want it to be accurate, okay, and precise. So we want them all to be, okay, bunched up in the middle. That's accurate and precise. Okay. Okay, statistical terminology. We say that an estimator is biased, okay, when it is not accurate. Okay, your aim is off. Okay, not accurate, your aim is off. We say that it is, we call it biased. It's a biased estimator. It's unbiased when the estimator is accurate, okay, i.e. that is correctly centered on our population parameter of interest. It's centered. It may be out from the center, okay, but we did aim for the center, and that was our goal. We hit our goal. Okay, for one of them, we didn't get as close for the other, but it's still accurate. We're still hitting the board. Okay, so there are degrees of accuracy. Sampling distribution, the distribution of a statistic. Okay, that's the sampling distribution. That's the distribution of a statistic. Before, we had the distribution of just a sample. Okay, sampling distribution. This is a distribution of a bunch of samples. Okay, before we had just a distribution of a sample, one sample. Now we're taking kind of an aggregate of a bunch of samples. It's the distribution of a bunch of samples. Okay, it's not just one sample. It's of the whole statistic. Okay, it's of the whole statistic. Example: the sampling distribution of X bar would show all the possible values X bar can take, okay, for a given sample size N, and how often we see it. Okay, so for example, okay, say that we were looking for let's take X bar. Okay, we were looking for the distribution of X bar, which is the sample mean. Okay, and we had sample sizes of, say, N is equal to 30. Okay, well, if I were to plot this on a graph, I would get, you know, maybe we would say that one of these would be, I don't know, 76. We'll say 76 was one of our sample means. We took 30 people or 30 items, and we ran the mean on that, and we got one data value. Okay, that's not a distribution. That doesn't make a distribution. That's just a sample. That's just a statistic of one sample. Okay, but what we're going to see is that when we run this over and over and over again, and say that we take 10,000 samples, right? 10,000 samples, then we might get a dot here, a dot here, a dot here, a dot here, a dot here. You know, maybe this is 78, maybe this is 80. Okay, we would get an average here and here. Okay, and then we get another average, and then we would start filling this thing in. Okay, and what we're going to see is that the true mean, okay, and the sample mean, okay, the population is approximately normal if we run this a bunch of times. Okay, if we have enough samples, okay, and our sample size is large enough, our sample size has to be large enough, then it is approximately normal. The distribution, this is the distribution of X bar. We call that the distribution of X bar. Okay, for this given scenario. Okay. Okay, and we'll say that basically all roads lead to a normal distribution if our sample size is big enough and we have run enough samples. Okay, we're going to let our samples go to infinity to give us a nice smooth curve. Okay, sampling distribution. By looking at the sampling distribution of a statistic, we can see how good of an estimator the statistic is in estimating the parameter. Okay, so here are some parameters that we have worked with, okay, in the past. Okay, is the population mean. Okay, population mean, and then the statistic is the sample mean. Okay, what we want to estimate is the population mean. What we use to estimate that is the statistic, or X bar. That's the sample mean. Okay, population standard deviation. Okay, what we want to use to estimate, and the sample standard deviation, S. Population variance is just the standard deviation squared, and the sample variance is just our sample standard deviation squared. Okay, and then the population of a proportion is P, Okay, the proportion of a sample, this again is just a sample. Okay, this is of the population. This is just a sample. Again, if we look at the sample, okay, so the population is P for proportions, the sample is P hat. Whereas for the population, for mean is mu and the sample is X bar. Okay, and so if we get a bunch of X bars, enough X bars, we'll be able to see, right? We'll be able to see, say that this is X bar 1, and then we get X bar 2. Oh, that's a little too small. Sorry, and we get X bar 2. Okay, and then we get a bunch of those averages. We'll see that we'll cover basically in most of the entire population if we take enough samples. Okay, and so we can say something about the distribution of the original population. Okay. Okay, other notation that we need to be aware of, mu of X bar, this is the mean of all the possible X bars. So if I do X bar 1, X bar 2, X bar 3, and I just keep grabbing these sample means, okay, these are sample means. Okay, then the average of the averages, this is basically the average of the averages, the mean of all possible X bars, we call mu X bar. The standard deviation of X bar is the standard deviation of all the possible sample means. Okay, and N is the sample size. Okay, that we're going to use. Okay, so let's deal with just means for right now. We'll get to the proportions in a little bit. Okay, but I just want to focus on the means. So we'll save this stuff. Let's just focus right on this for now. Okay, so the mean of our sampling distribution, if I do this process of taking samples and samples and samples and samples and samples and samples, all of the same size, okay, samples and samples and samples, okay, then the mean of our sampling distribution is going to be equal to the mean of the population. So if I have the entire population, okay, and it has a mean, then the mean of all of the samples, okay, the mean of all of the samples, this is the mean of the population. The mean of all of the samples will also be, okay, the mean, okay, of all the samples. The samples and the population mean, they'll be equal. They'll be the same value. They'll be right in the middle here. Okay. However, the standard deviation of all the values of X bar, okay, standard deviation of all the values of X bar, will be divided by the square root of the sample size. So that is dependent upon the variation here. Okay, so say that the sample size was 1, well, that would just be the standard deviation. Okay, because you would only have one sample that you're finding standard deviation. But then if I take all of the sample means and then I take the standard deviation, I have to divide by the sample size. Okay, the square root of the sample size. And what that does is that it makes a thinner, okay, it actually makes a thinner one. Maybe I'll put this in a different color. Okay, it makes a thinner, okay, a thinner graph, a thinner distribution. Okay, now the mean is the same spot, but the standard deviation is smaller because I divided by the square root of the sample size. Okay, I divided by a number bigger than 1. And so that makes this a smaller standard deviation. So whereas before the standard deviation was for, okay, the red one, we'll say the red one was the original distribution. The purple one Okay, so this is the, for the sample means. Okay, sorry, that was mu. Okay, but here the standard deviation, mu of x bar, is equal to the original standard deviation divided by the square root of the sample size. And that's how I get my new standard deviation. Okay, now the central limit theorem says, okay, the shape of our sampling distribution is normal if, okay, it's normal if, okay, of sample means, okay, the distribution of sample means will approximately be normal if, one, we already knew that the population was normal. We know that we were given a normal population to begin with, then we're just going to stay with a normal population. Or if it wasn't a normal population to begin with, okay, then the sample size is at least 30, okay, is at least 30. If the sample size is at least 30, then the distribution, the x bars, will say, are normal. Okay, then the x bars will create a normal. So even if I start off, okay, say that the original population was not normal, if my sample sizes is long enough and I take averages, because remember, this purple distribution up here, that's the distribution of the averages. Okay, that's the distribution of the averages. So what I'm doing is I'm taking a bunch of averages and I'm putting them into a distribution. If I do that, if I take all these distribution of averages, then that becomes a normal distribution. Okay, whereas before, say that the original distribution looked like this. Okay, had some outliers out here. Okay, so we'll say that this is the original. Okay, and where's the mean? Where's the mean of the population? The mean of the population is here, maybe. Okay, the average is here. That's the mean of the population. But what's the distribution of the sample means going to look like? Well, that guy will actually be, well, mine's not normal. Let me go back to this guy here. This one is skewed right? Okay, it has a right tail. Okay, let's go back to this guy here. Okay, and this guy is normal. Okay, so whereas the purple one, okay, that's the distribution of the sample means. Okay, whereas the original was the population. So say the population had a bunch of outliers over here, right? So we have some outliers. Okay, outliers. But what happens when I have outliers and I take all of the averages? Well, aren't those outliers going to be averaged? Aren't I going to get an average value that kind of undoes those outliers, right? Like say I have a really big value up here, well, that's going to be counteracted by the small values over here. And so my mean, my average will be, the average of the averages will be in the same spot as the original average, but the distribution will be a normal distribution. It will end up being symmetric. Okay, so this is the distribution of the sample means, is the purple one. So this is the distribution of the sample means. And it's means plural. It's not just one mean. It's not a sample mean of just one sample. It's samples upon samples upon samples upon samples upon samples, and then you fill it all in and you get this nice normal curve. Okay, it's the distribution of the sample means. okay? And for the sample mean, mu of x bar, okay, is equal to mu, that's the original population mean, okay? And the standard deviation of x bar is equal to the original standard deviation over the square root of n, okay? And so, and then this is normal. This is normal if, okay, n is greater than or equal to 30, or if we already knew that the population was normal. Okay. Okay, so let's see how this works in practice. I'm going to skip the next one. Okay, we'll come back to proportions. I don't want to confuse means and proportions right now. We'll come back to the proportions. Skip the next thing about proportions. Okay, let's go to example 1. Okay, so the distribution of the population mean of mu is equal to 30, and a population has mean mu equals 30 and standard deviation of sigma equals 2.5. And it is slightly skewed to the right. Okay, so it's slightly skewed to the right. A sample size of n equals 40 is randomly selected from this population. Describe the sampling distribution of x bar. Okay, so what do we know? We know that the sample size is larger than 30, right? The n is greater than 30. So n is equal to 40, which is greater than 30. So that means that the sample distribution, okay, of the sample means, okay, x bars, all the x bars, if I were to take, so again, this is what I'm doing here is I'm saying out of, say, a population of maybe 1,000, okay, what are we doing? We're taking a sample of 40 and we're finding the average. We're taking another sample of 40 and we're finding the average. We're taking another sample of 40 and we're finding the average. And we're taking another sample of 40 and we're finding the average. And we're taking another sample of 40 and we're finding the average. And we're getting all of these averages. Okay, and when I do all of these averages of the original, I could have some really high numbers, but they're going to get counterbalanced by, you know, some low numbers as well. And it's going to, as an aggregate, it's going to end up being a normal distribution. Okay, so this is sample distribution of sample means is normal, okay, or nearly normal, okay, with what? With mu of x bar equaling the original mu. Well, what was the original, what's the mu of the population? It's 30. Okay. And what is what is the standard deviation of the sample means? Not the sample means. Well, it's the standard deviation of the sample, which is 2.5, over the square root of the sample size. Okay, and this comes out to be approximately 0.395. So whereas the original standard deviation was 2.5, the new standard deviation is much smaller. It's only 0.395, a much smaller standard deviation, but it creates a nearly normal graph. Okay. Okay, let's try example 2. Okay, population has a proportion. Oh no, let's skip 2. Okay, let's go to 3. Okay, let's do 3 with our sample means. Okay, when designing life rafts, an obvious important consideration is the weight capacity. SAC Shipping purchases life rafts that have a capacity of 16 passengers and a total weight of 2,400 pounds. Suppose a life raft is loaded to capacity of 2,400 pounds with 16 males. Okay, so find the mean weight of the passengers. Okay, well, the average weight of the passenger is going to be 2,400 divided by 16. Okay, that's X bar. Okay. Okay, so what does this end up being? 2,400 divided by 16. It's 150. Okay. Okay, it's 150. Okay. Okay. Now it says find the probability that one randomly selected adult male has a weight greater than 150 pounds. Okay, so the mean weight of the passengers is 150. Find the probability that one, so this is just one randomly selected adult male has the weight of greater than 150. So this is just one. So what's the sample? The sample size, okay, is 1. Okay, sample size is 1. That's it. Okay. Okay. And so what's the population? What's the population? What's mu for, what are we looking for? Males? Males, right? What's the population mu for males? The mu for males is 182.3, right? Okay. So we have a sample size of 1, I'll just say that n is equal to 1. Okay, so n is equal to 1 in this case. Okay, and so mu of x is equal to 182.3, because that's going to be the same as the population, right? Population. So I'm getting that from the chart here. Up there, there's the population. Okay, the shape is normal. We know that it's normal. Now, what's the shape of the sample, of the sample means here, of the sample mean? Okay, what's the shape of the sample mean? Well, n is not greater than 30. N is not greater than or equal to 30. But what do we know about the original population? Do we have a, I wrote the wrong number for mx, or mu x, x bar, sorry. No, right, did I? I don't think so. Let me see. So and the mean weight of the passengers, okay, so that's the mean weight of the passengers, okay, of these passengers, right? So the mean of the entire distribution, okay, the mean of the entire distribution should be the same as the mean of the entire population. Okay, so it's correct, I think. Okay. Thing. Yeah, mu x. Okay, so obviously there's a question on this, right? Okay, so let's go back. Okay, it says that the shape is normal, right? So the original, let's do the original and the new one. Okay.
Yes, sir.
Yeah.
Sorry, I think we're just talking about in section B when you wrote m of x, you
It's
wrote it equals
mu x, yeah,
182.8.
equals 182 point, oh, sorry. It's the 0.8 that was messing people up.
Yes,
Oh, I'm sorry. Thank you.
you're welcome.
Okay. I thought it was, you were talking about the 150. Okay. Okay, so yeah, so mu of x, so again, it'd be good to go over the shape of these. Okay, the original one is 182. Okay, so where's my pens? There. Okay, so the original, well, what do we know about the original? We know that the original one, okay, is normal. Okay, this is the population. And it had mu, okay, of 182.3. Okay. And it says, what is the probability that one randomly selected adult male has a weight greater than 150 pounds? So I was saying that n is equal to 1, mu of x is equal to 182.3, right? Because the new one is still going to be normal, okay? And it's going to be 182.3. Mu of x bar, it should be x bar. Okay, mu of x bar is equal to 182.3. Okay, and at the same time, what's going to be my new sigma x bar? Well, it's going to be sigma over the square root of my sample size. Well, what's my sample size? It's 1, right? Okay, and so that's just going to be sigma. So they're basically going to be the same distribution because why? Because what am I doing here? I'm taking samples of size 1. Well, how does that make sense that these are the exact same? Well, if every single plot, every single value that could possibly exist in the original one here, okay, that little point here is of sample size 1, right? So how do you average a sample of size 1? Well, it's just that sample. It's just that one value, right? And so that one value would then, if we ran, thousands and thousands of samples here, it would populate the exact same thing. This thing would just get translated over here, right? And it would build the exact same one-to-one population. Okay, so the sample means here are just, a one-to-one correspondence to the population. Okay, so this is the distribution of the sample means down here. Okay, so let me write that a little bit better. Okay, so, and again, we see that here n is not equal to a number bigger than 30. So, okay, n is not greater than or equal to 30. But what do we know? But the parent function or the parent distribution was normal. So the sample distribution is, so the x bars are also normal. Okay, so the x bars are also normal. So how do I find the probability of one person, okay, being greater than 150 pounds? Well, that's the total area under the normal distribution. And how did we find the total area under the normal distribution? Normal CDF. Okay, normal CDF. Okay, where are we starting? We're starting at 150 and we're going to infinity. Okay, and we want the probability that one of these people is, okay, 150 or larger. What's the probability that one of these people are 150 or larger? Okay, then, and what's the mean? What's the mean? Well, it's 182.3. And what's the standard deviation? Well, the standard deviation is just the standard deviation of, okay, of the original distribution. Well, that's 43.8. Okay, so this is the probability that x is greater than or equal to 150. Okay, and so I just plug that into my calculator. Let's go to the calculator. Move this up. Okay, let's go to the calculator here. Okay, let me turn this on. And so I'm going to do normal CDF. Okay, second floors. Okay, normal CDF, arrow down. Okay, and the lower is 150. We want everything from 150 or above. We want greater than. What's the probability that one of these people is greater than 150? Okay, and that's 150 to upper, which is infinity. So that's that e to the 99. Okay, and then what's mu? Mu is 182. 0.3. Okay, and the standard deviation is 43.8. I'm going to paste that and then calculate it. And it comes out to be, okay, 0.7696, I believe. Okay, yep, 7696. Okay, or about 76% chance, 77% chance. Okay, there's a 77% chance of somebody being above 150. Okay, which means that, okay, we're probably not going to be able to fill the thing to capacity. Okay, you're not going to be able to fill that raft to capacity because there's a 77% chance that, you know, any one of these people is above that 150 mark. Okay, so now what happens when, okay, part C, find the probability that a sample of 16 randomly selected adult males has a mean weight of 150 pounds. A mean weight greater than 150 pounds. Now I want to know what happens when I take a larger sample size, not just 1-to-1. What happens when I take a larger sample size? Well, what's going to happen is we have to divide by the square root of n, right? Divide by the square root of n, and n in this case is no longer 1. It is larger than 1. It is 16, which is still less than 30. Okay, this is still not greater than 30. But again, the population distribution is normal. Okay, and so I know that the population is normal, and so I can still use the central limit theorem to say, hey, this is going to be approximately normal when I take the distribution of the means. Okay, so if we take 16, a sample size of 16, okay, then we end up with a similar distribution as before, but it's much narrower. Okay, it's much narrower. Still, the mean is 182.3, but the standard deviation went down by 1/4. Okay, so how did it go down by 1/4? Well, the new standard deviation for the means, okay, the means is the original standard deviation divided by the square root of n. The original standard deviation was 43.8, but now it's divided by the square root of 16, which is 43.8 divided by 4. Okay, which is about 10.95. If you do that on a calculator, okay, 43.8 divided by 4, okay, is 10.95. So the standard deviation is much smaller now, okay? So much smaller standard deviation, okay, than before. That means the probability of getting someone above 150 it's going to be much bigger. And it's not just someone above the 150, but getting, what's the probability of getting, okay, at least one out of the 16 people, okay, if you're, because you're taking groups of 16, right? You're taking groups of 16, you're taking groups of 16. So what's the probability that of those 16, your mean is going to be bigger than 150. Your average is going to be bigger than 150. Okay, well, it's going to be pretty high. So let's take the probability that the mean, okay, the mean is greater than 150, okay, pounds. Given that we've increased our sample size from 1 to 16, okay, so that's normal CDF, right? So normal CDF, okay, of 150 E 99. The mean is the same, it's 182.3, and the standard deviation is 10.95. So I don't know how far back, okay, so how did we know the original distribution was normal from the start? Yeah, because it tells us back here, okay, oh, at the bottom here, it says the shape for the males is normal. Okay, so good question. It told us that the shape was normal. Now, if it told us the shape wasn't normal, then in order to do any of this stuff, I would have had to take a sample size bigger than 30, okay, bigger than 30. But I can still take sample sizes that are less than 30, even though we know that even though it's less than 30, because we know that the original population, this is the original population, is normal. Okay, so that's how we got this guy over here. Okay. Okay, sounds good. Okay, good question. Okay. Okay, let's talk about sample proportions. Okay, sample proportions. How do sample proportions differ, okay, from sample means? Okay, well, they're not too different. Okay, sample proportions, okay, are still going to be, okay, as we take our proportions, okay, it is going to be, as long as my sample proportion, or sorry, as long as my sample size is large enough, okay, as long as the sample size is large enough, then all roads again lead to a normal distribution, okay? And it will lead to a normal distribution where my mean, okay, my mean of my sample proportions is equal to my population proportion. Remember, this is the population proportion. Population proportion. Okay, this means the mean of the sample proportion. Okay, so the mean of the sample proportion, the average of the sample proportion, is equal to the population proportion. Okay, very similar to the means, right? So very similar to the means. So but the proportion, a proportion is a number between 0 and 1. So just keep that in mind. Okay, so this is a number between 0 and 1. Okay, whereas the other one is just a number. Okay, usually a number that's positive. Okay, but this is a ratio. This is a ratio of two values. Okay, the sample standard deviation, okay, and the standard deviation for the sample proportions, okay, again, sample proportion, okay, p hat is sample proportion, okay, the standard deviation of the sample proportions is going to be equal to the population proportion times its complement. Okay, Q is the complement. So what does Q equal? Q is equal to 1 minus P. That's what Q is. Q is equal to 1 minus P. It's 1 minus. So if say P was equal to 0.73, then Q is the complement of 0.27. You see how those add up to 1? Okay, and what's N? N would be the sample size. N is the sample size, right? So I'll just put an arrow and just say N is sample size. Sample size. Oops. Okay, sample size. Okay, so the standard deviation here, okay, is equal to the square root of P times Q over N. Okay, so P is the original population proportion, P is population proportion, Q is 1 minus the population proportion and divided by the sample standard deviation, or sorry, divide by the sample size will give me, when I square root it, the sample proportion standard deviation. Okay. Okay, let's do a problem with this. Okay. Now, again, how do we know this is going to be normal? Well, again, the sample size has to be large enough. And what's large enough for proportions is that N times P has to be bigger than 10, and N times Q has to be bigger than 10. So, for example, if the sample says, say in the last, say that P was 0.73, right? So let's let P equal 0.73, right? 0.73. So is a sample size of 10 big enough? Is the sample size of 10 big enough? Well, what's 10 times 0.73? Well, that's 7.3, and that certainly is not bigger than 10. And so that's not big enough. So a sample size of 10 is nearly not large enough. Okay, but what about out of sample size of 20? What if N is equal to 20? Is that going to give me a normal? Okay, it's approximately normal if N times P is greater than 10, or sorry, and N times Q is greater than 10. Okay, so both of them. Now whichever one's bigger, okay, I know that if P is bigger than Q, then if I multiply P times N, well, that's going to be, you know, the biggest one. So I always want to go with whichever one's the biggest. If P is less than Q, then I would want to go with Q. Okay. But I'm just going to say, oh, okay, if is 20 times 0.73, which is equal to what? 14.6. Okay, is that greater than 10, greater than or equal to 10? Then yes. What about the other one is 20? That's a 20, by the way. Okay. 20 times 0.27, okay, which is what, 5.4? Okay, is that greater than or equal to 10? No. Okay, that one's not either. So 20 isn't even big enough yet. Okay, so we want to multiply it by, okay, whichever one is smaller, okay, because both of them have to be bigger. Okay, both of them have to be bigger than 10. So we need a pretty large sample size. Okay, so even though one qualifies, the other does not. Okay, and so what would be a big enough sample size? Well, what if we did 200 here? Well, then we would get, okay, if we did 200, sample size of 200, then we should be in the clear. If we do 200, then we're going to get 146 and 54, which are both bigger than 10. And so we're clear. Okay, then it's normal. Then it's normal. Okay, so we have to check our sample size. Is it big enough? Is the sample size big enough for our population or for our sample proportions? Okay. Okay, here a population has a proportion of 0.75 and a sample size of 115 is randomly selected from this population. Describe the sampling distribution of P hat. Okay, so what's the sampling distribution of P hat going to look like? Well, what's mu of P hat? Well, isn't that the same thing as P? Isn't that going to be my 0.75, right? So this guy here is mu of P hat, which is the same as my population proportion, which is 0.75. 0.75. That's my middle. That's my mean. Okay. 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 Now, is this going to be normal? Can we use the central limit theorem here? Well, I have to make sure that my sample size is large enough. Okay, is my sample size large enough? Okay, so is n times p, which is equal to 0.75 times 115, is that bigger than 10? Well, everybody okay? Am I back? Okay. 0.75, okay, times 115, okay, is 86.25, which is bigger than 10, so that checks. Now what about the smaller one? Again, we really only have to check the smaller one, 0.25. Where did I get the 0.25 from? Well, it's 1 minus p, okay, n times q, which is n times 1 minus p. Let me write that nicer. Oops, not g, q. Okay, n times 1 minus p, which is n times 1 minus 0.75. Okay. Be 28.75. If I do that one, 0.25 times 115. Okay, is 28.75, which is greater than 10. And so that checks as well. I'm off the side of the thing. Not 16. Greater than 10, so that checks. Okay, and I'm going to reverse this. This should be reversed. 115 times 0.75. There. Okay, so since the conditions are met, then p hat, okay, then nearly normal. Okay, with Okay, mu of p hat equaling 0.75. And then what's sigma of p hat going to equal? Sigma of p hat. Well, we got to go back to that formula. Okay, sigma p hat is radical p times q over n. Okay, so radical p, okay, radical p, that's 0.75 times q, which is 0.25, over n, and n is 115. So I'm going to plug all of that in. Okay, so hopefully you can see that okay. 0.75 times 0.25, okay, all over 115. I'm going to plug that into the calculator. So that's the square root of, maybe I'll put a parenthesis here because I'm dividing, 0.75, okay, times 0.25 divided by the denominator, which is 115. Okay, and I get about 0.04, which is about 0.04. So about 0.043 there. Okay, so it's nearly normal with mu p equaling 0.75, so that's the mean, and the standard deviation is 0.04. Okay. Okay, and we'll say sigma p is equal to 0.04. Okay, so mu of p is equal to 0.75, sigma p, which is would be one standard deviation out, right? One standard deviation out would be 0.04. So let me write this down here a little bit. Lost my graph. See if I can edit this. Okay, and so since the standard deviation is 0.04, how would I get one standard deviation away from the mean? Well, wouldn't I add 0.04? So if we were to look at the graph here, it would be 0.75 and then 0.79, right? And that would be one standard deviation. Two standard deviations, I would add another 4, that would be 0.83. Okay, that would be two standard deviations. And then 3 would be the almost the entire graph, which again I would go up 0.04 again, that would be 0.87. Okay, and then if I go down 1, that's 0.71. Go down 1 again, that's 0.67. And then go down 1 again. Okay, so this is minus 1 standard deviation plus 1 standard deviation. This is minus 2 plus 2. This is minus 3 plus 3. And then this is going to be 0.63. Okay. Yeah. We have questions? Sorry. Okay. Can you go over why we do n minus 1, or sorry, vice versa for P and Q? Okay. So it's 1 minus P is equal to Q. So that's how I get Q. Okay, so how we get Q is 1 minus P. Okay, that's how we get Q. So, and then we use Q for the standard deviation, and we use Q to check if we can actually use the normal distribution. Now, what if this fails? Well, then we're stuck. We can't do anything. We cannot do any more computation. If this thing fails, if the sample size is too small, then we're done. Then there's no computation that can be done. You know, even if we had something down here and we wanted to find out what's the probability of something happening, well, we can't do it if the sample size isn't big enough. Okay. So hopefully that answers your question. I don't know if that was your question or not. So it's 1 minus P is Q. So I don't know if you got confused with N there, but and then it's divided by N. Are you asking on the calculator, like what we did? So, okay, just let me know.
That answers my question. Thank you.
Oh, okay, sounds good. Thank you. Okay. Okay, let's go over this one here, example 4. Okay, a large university with over 25,000 students has 73% of the student population drives to school. Okay, so what does that 73% represent? Well, that's the population, right? So that would be P is 0.73. Okay, so that's P equals to 0.73. Okay. Suppose that the parking and and 25,000 students, that is not N. Okay, N is actually the entire, this is the entire student population. That's you know, the entire, this is large N, not little n. Okay, this thing here is large N. Suppose that the parking and transportation department doesn't know this information, so they conduct a survey of 1,000 randomly selected students and ask them whether or not they drive to school. Okay, so we're conducting, out of the 25,000, we have a sample, okay, a sample of 1,000 students. So that's little n. Okay, and that's what I need to work with, is little n here. Okay, I don't care about big N, I care about little n. Okay, lowercase n, not capital N. Verify that the distribution of P hat is approximately normal. Okay, so is P hat approximately normal? So is N times P, okay, greater than 10? Okay, and is N times Q greater than 10? Okay, so our sample size N is 1,000, so we have 1,000 times P, which is 0.73, which if I multiply that together, that's 730, which is certainly greater than 10. Okay, now what about Q? Well, what would Q be? Q is equal to 1 minus P, which is 1 minus 0.73, which if I do that on the calculator, 1 minus 0.73 is equal to 0.27, what we were working with before. Okay, so that's Q. So what about the smaller one, Q? Is N times Q, or 1,000 times 0.27, is that, not Z, okay, 0.27. Is that going to be bigger than 10? Well, that's 270, which is certainly bigger than 10. Okay, so both of these check. Okay. Okay, so it is approximate normal since conditions are met. Distribution is normal. Is normal. Okay, so the distribution is normal. Okay, what is the probability that P hat will be more than 3% away from the true population. Okay, so we have the population, okay, of 25,000 students, but we're interested in our sample proportions, Verify that the sample proportion, okay, was approximately normal, okay? And what's the probability that the sample proportion, not the original proportion, the sample proportion is more than 3% away from the true proportion? Okay, well, the sample mean and the true mean and the true proportion are the same thing. The sample mean, okay, and the true proportion. So the sample of p hat is equal to p, right? Okay, the mean of the sample proportions is equal to the true proportion. Okay, well, what was the true proportion? The true proportion was 0.73. Let me write this down here. So the middle here is going to be 0.73. That's the middle. Okay, the mean. Mu of p hat is equal to p, which is 0.73. Now, what's within 3%? What's within 3%? Well, within 3% is going to be 0.76 up to 0.76 and down to 0.70. So what this is really asking is I want the probability that the sample proportion is between 0.70 and 0.76. It's somewhere between 0.70 and 0.76. Okay. Okay, so I need to calculate the mean, but I also have to calculate the standard deviation. I need to know, well, how many standard deviations away are these guys, and use that in my computation. Well, the standard deviation for the proportion is equal to the square root of p times q over n. Okay. So what's p? P was 0.73, 0.27 was q, and n was 1,000. Okay. Oops. Okay, I think I wrote this backwards. The standard deviation is fine. It says that it will be more than 3% away. I read it backwards, sorry. We want more than 3% away. So it's these areas that I'm looking for. Okay, so it's not this. It's the probability that x is, or p hat, probability that p hat is less than 0.70 or p hat is greater than 0.76. Okay, so we want more than 3%. If we want it the other way, it would say within 3%. I misread it. Okay, at any rate, I just want to make sure I set that up properly. Okay, so if I plug this into a calculator, 0.73 times 0.27 over 1,000 and square root that, I get about 0.014 for my standard deviation. So using the mean and the standard deviation. Now I'm going to calculate I'm going to calculate these individually. Okay, so I'm going to calculate this guy. Okay, p hat is less than 0.70. Okay, and p hat greater than 0.76. I'll calculate those individually. What we're going to see is that they are the same area. They are the same area. Why? Because they're the same amount away from the mean. They're the same amount of distance away from the mean, and so we would get the same value on one side as we get on the other side. So we really would only have to calculate one of them and then multiply by 2. If we calculate one of them and multiply by 2, we should get the same thing as taking them individually and adding them together. Whichever way we want to do it, that's fine. Maybe I'll do it both ways, just so that we're good. So if we want p hat is less than 0.70, then what is that? Well, that's normal CDF, okay, of negative 1e, or negative e, we'll just say, negative E99 to 0.70. My mean was 0.73, and my standard deviation is going to be 0.014. Okay, and so that's approximately, let's go to the calculator. Turn on. Okay, second VARS, normal CDF. Okay, the lower I want as negative E, negative comma, second comma, E99. The upper I want as 0.70. Oops, 0.70. The mean I want as 0.73. And the standard deviation I want as 0.014. Okay, I'm going to paste that, and I get about 0.016, about 0.016. Okay, so this would be equal to, this guy is this, okay, just that one piece is that. This is 0.016, okay, over here. Now again, if we did the exact same calculation, maybe I'll just do that on the calculator and not write it down. But if we did the exact same calculation for this guy, what's greater than 0.76, I would change the order in which I'm doing this here. Okay, I would say that from 0.76 to infinity, okay, the mean is the same thing, the standard deviation is the same thing, and we hit enter and we get the exact same number, right? So this would be 0.016 plus 0.016, okay, which is equal to 0.032. So that would be the probability, okay, that I would be 3% away from the true proportion. Okay, or I could just multiply 2 times that number. Because again, because of symmetry, they're the same. Okay, draw a picture that summarizes the central limit theorem for means and proportions. Okay, explain your picture. Okay, so let's summarize. Okay, so for means, so for sample means, let's draw one picture. Okay, if the sample size is large enough, okay, then it's approximately normal. Okay, so for sample means, okay, we have mu of x bar is in the middle. Okay, and we have, okay, going out, standard deviations. Okay, standard deviation here, sigma x bar is the standard deviation, and in order for this to be true, one, the parent population, or the parent distribution is normal, or two, the sample size n is greater than or equal to 30, which we didn't do any of those for the sample size. We did do one for the proportions. Okay, what about for the sample proportion? Well, for the sample proportion, let's summarize what we learned about the sample proportion was that it is nearly normal if, Okay, it is nearly normal with mu of p hat equaling p, okay, the population proportion, and sigma, okay, sigma of p hat, okay, equaling the square root of p times q over n. Okay, and then over here with the mean, this was sigma over the square root of n. Okay. Okay, so this is just equal to mu as well. Okay, and oops. Unmute me. Now I should be unmuted. Okay, are we good? Yes. Okay, sorry about that. I don't know how I got muted. Okay, good, thank you. Okay. Thanks. Okay, so for sample proportion, we learned that, okay, for the mean, it was equal to the population proportion, and the standard deviation, oops, wrong color. Okay, and the standard deviation was the square root of p times q over n. Okay, and it is nearly normal. Okay, it is normal only if n times p is greater than 10, greater than or equal to 10, and n times q is greater than 10. So that's the summary here. Okay.